Hey guys, today we're going to be talking about graph features. Hopefully we all remember how to plug things into the y equals button on our calculators to get the pictures of the functions for us. Today what we're going to do is we're going to talk about some specific graph features, some specific vocabulary that goes along with it, and in many cases how to calculate these algebraically. So the first two vocabulary words that we're going to talk about are the x and y-intercept, the x-intercept being the point where we cross the x-axis, and the y-intercept being the point where we cross the y-axis. So if we take a look at this graph, obviously my y-axis is going up and down, so this right here is going to be my y-intercept. So that is the point 0, -2. This is my x-axis going horizontally. We are crossing the x-axis at 2. So we get the point 2, 0. All right. So if we want to find the x and y intercepts algebraically, we have to use this fundamental feature of the 0 to help us do that. We know that the coordinate for any x-intercept is going to be an x value, 0, meaning that I can plug a y value into our function to solve for the corresponding x value. So 4x plus 0 is equal to 5. 4x is equal to 5. X is going to be equal to 5/4 in this case. So my graph should cross my x-axis at 5/4 with the point 5/4, 0. If I want my y-intercept, we hopefully should know that every y-intercept has the format 0, y, which means we can plug in 0 for my x value. So if I do that here, I get that my y is equal to 5, meaning my graph will cross at 5 on the y-axis and hit the point, the coordinate 0, 5. All right, so that's x and y intercepts. Now, this is a linear function. X and y intercepts also occur in parabolas or our quadratic functions. They occur in many different functions that we're going to be looking at. So if they ever ask you for the x and y intercept, it's the same concept, right? The x-intercept is the place where we cross our x-axis, which in this case, there's actually 2 points that satisfy that. There's the point -3, 0, and the point -1, 0. All right. Still the same idea that we're crossing the x-axis, but it changes with a parabola in that we end up with 2, sometimes 1, sometimes no x-intercepts on the graph. The y-intercept is still going to be the place where I cross my y-axis, so that's going to be right here, and that's going to be the ordered pair 0, 3. All right, so we can find these pieces of information for all different types of graphs. But what's specific to our quadratic, at least the way we're going to be looking at, are the zeros, the vertex, and the axis of symmetry. Okay, what do we remember about zeros? Well, zeros are the place where our function value is equal to 0. Now, the one thing we should remember about function value is that f of x is equal to y. So what this is basically saying is we are looking for the points where y is equal to 0. So looking at our graph, where is y equal to 0? Well, it's equal to 0 at my x-intercepts, okay? So you will notice that the zeros of the function, at least the real zeros, will correspond to the x-intercepts, okay? Now, what is my x-intercept here? It's -3, 0, -1, 0. That's if they ask for the coordinate of your zeros, or if they just ask you for the zeros themselves, it's going to just be my x values. Okay, so zeros will be these x-intercepts. Where's my vertex? Well, remember the vertex is the point on the graph that divides it completely in half so that we have a mirror image on both sides. So if we take a look at this graph, our vertex is going to be this point right here. Okay, so what is it on this graph? Well, we look at the point. -2 for my x, oops, comma, -1 for my y. Okay, so that's my vertex point. Now, specifically for this parabola, my vertex is going to be a minimum. So you might see those words interchangeable. If the parabola is upside down, this vertex might be called my maximum. Okay, but these words are all referencing that same point that kind of divides our graph in half. Now, also on this graph, we should see this dashed red line. Okay, this dashed red line is not necessarily a part of the graph. That's why it's written dash. Doesn't satisfy the function, but it provides that halfway boundary to show the symmetry of the graph. We call that line the axis of symmetry. Okay, and the axis of symmetry is a vertical line, so it's an x equals line at the value, in this case, -2. Okay, so what we should notice is that the x value of the vertex and the x value that we choose for our axis of symmetry should be the same. Okay, because the axis of symmetry divides my graph in half and cuts through my vertex value. Okay, so we should be able to pick these out of any graph that we see. But how about finding it algebraically? How do we do this? Well, there is a formula for finding the axis of symmetry. Right, remember it is an x equals equation, and it's x equals to -b over 2a, where a, x squared, plus b, x plus c, represents a parabola in standard form. So we want the coefficient of x squared in our denominator and the coefficient of x in our numerator. So how do I fill this out? Well, what is my a? Is 1. My b is -12, and my c is 46. To find the axis of symmetry, I plug in -12 for b, 1 for a. I get 12 over 2. I get x is equal to 6. Okay, so this graph will have its halfway point at x is equal to 6. Right, so that is my axis of symmetry. Now, hopefully what we should remember is that my vertex goes, the axis of symmetry goes through my vertex. So this x value here for my axis of symmetry is actually going to be the x value of my vertex. So what's left? We have to find the corresponding y value. And we do that by plugging it into the function. So what is my y value when x is equal to 6? Plus 46. Well, let's type this into the calculator. So we got 6 squared minus 12 times 6 plus 46 is equal to 10. So what is the coordinate of my vertex? It's 6, 10. All right, so this is the formula you would need for the axis of symmetry, and that is how we would find the vertex from there. Okay. Now, we will be talking about finding the zeros algebraically when we talk about solving quadratics, but for now, what you need to remember is how, if it doesn't work out to a nice number, how do we find these zeros on our calculators? Okay, because everybody has the TI-84 plus CE, so we should be able to find these values. So the first thing you always want to do is you want to put the equation in standard form if it is not equal to it. Okay, so in this case we have 3x squared minus 12x minus 4 plugged into my calculator into the y equals button. Okay, the zeros, remember, are the x-intercepts. So if it doesn't fit on my screen, you can adjust the screen by zooming in, zooming out, doing zoom standard, changing the window, whatever you need to see those x-intercepts. Now, we see on our particular screen, now our graph obviously goes a little bit further down below for our vertex, but we do see that we have two x-intercepts there, so we can proceed without adjusting the screen. Okay, now when we do this, to find the zeros, we're going to press second trace. Okay, the same graphing menu we've been looking at all year. And we're going to choose option number 2, which states 0. Okay, that will give you any 0, any x-intercept value that we need. Okay, now when this happens, it will prompt you for a left bound, a right bound for the desired 0. The idea of these left and right bounds, which we'll put these little arrows on the screen, is that the 0 that I'm looking for falls in between those two dashed lines, this line being my left bound, this side being my right bound. And at that point, they are going to ask you to take a guess. So you just press enter for that part. And you should get the 0 pop up on the screen. So at the bottom, we have x equals. Now, this does not work out to a nice value, but sometimes they'll ask you to estimate it. So let's just say round to the nearest hundredth, and we get the ordered pair 0.31. Now, of course, it is a quadratic, and for cubics we'll have 3, and quartics we'll have 4. So we want to make sure that we repeat this again for any extra zeros that we need. So second trace, option number 2, we set up our left bound, we set up our right bound, we make sure that 0 is in between, and we press enter. And again, we get this value at the bottom of the screen right here. Now notice this -1 E12. Remember, E on the calculator is just scientific notation. If it's a really big number, typically it just means that it's getting really, really close to 0. So what is the value rounded to the nearest hundredth? 31, 0. Okay, nice. We also can use the calculator to find the vertex. Now, this helps specifically when the vertex is not a nice, clean number. Okay, now I'm going to show it to you with nice numbers, but we can use this for any vertex, fraction form, or any other. But the key to the vertex is recognizing whether you have a maximum or a minimum. Now, anytime we have an a value, meaning the ax squared value, that is positive, aka greater than 0, my graph will open up and look like this graph below. And this graph that opens up has a minimum. Okay, so when we do the graphing application, we are going to choose minimum. When the a value is less than 0, or it is a negative value, the graph will look something like this one that I'm outlining. And that vertex point is going to be a maximum. So there is no vertex button on the calculator, but there is a max or a min button. So you want to make sure you press that. And again, this can be found when you press second and trace in that same calc menu. Okay, so once you've chosen whether it's a minimum or a maximum, you're going to do the same thing with the left bound, right bound idea, right? The left bound has to be to the left of the vertex. The right bound has to be to the right of the vertex that you're looking for. And at the bottom of the screen, we'll get the value. Now, whenever you see 0.999999999 like that, that's usually a rounding error of the calculator. So this has a minimum value at 3, -4, which also works as its vertex. Whereas over here, we have a maximum value of 2, 2, which is its vertex. All right. So we can find both of those using that particular menu that we see. Now, there's one other thing that we have to talk about with graphing, and that's transformations. Now, transformations are basically changes that are being made to a parent function. A parent function is what I would like to say the most simplest form of a particular equation, meaning there's nothing being added to it, multiplied to it. It's the purest form of an equation. So 3 functions we should be very familiar with are linear, quadratic, and cubic. Okay, their parent functions are the equations below, y equals x, right? That's the minimum qualification for something to be linear. So now, whatever line that you're looking at will be some alteration on this parent function. So whether you make the slope bigger and the line becomes steeper, whether you move the graph down or up to change the y-intercept, right? All of those things are going to be changes we make to parent functions. Okay, quadratic functions, hopefully you remember, give the shape of a parabola. Okay, and the most basic thing you need to be considered a quadratic function is that x squared. So that is your parent function. Again, this can flip, this can shift. So we're going to talk about how that happens. Cubic functions all have this general shape, right? It kind of goes up, has a little squiggle in the middle, and then continues going up. Sometimes when you add a lot of things to it, you'll get some nice big bumps, but in the end, they generally take the same shape, and it's very similar to this x cubed graph. Now, the ones you may not be as familiar with, well, maybe not absolute value, should know the absolute value parent function. Okay, that's y equals absolute value of x. It's a V shape. And you should be aware with the square root graph, okay, square root function, which basically looks like half of a parabola laying on its side. So it should not be so surprising to you that when we get to the cube root function, it's going to be the cubic function on its side. Okay, so notice if I took this graph up here and I turn it on its side, that's how I get this cube root function, okay? So we should be able to recognize these, including this exponential function, but I'll talk a little bit more specifically about that one. But we should be able to identify these general shapes by name, okay? So these are the ones that you want to make sure you have committed to your memory. You should be able to identify it from an equation. You should be able to identify it from a picture, etc. Now, the last one you need to know is exponential. And the reason I have exponential here separate is because I have a parent function of an exponential where we have a base 2. But the key feature of an exponential is that we have a numerical value as the base and x as our exponent. So another parent function could be 3 to the x. Another parent function could be 1/2 to the x, right? So the exponential function is special in that it can change for different bases, but they will all still have the same general shape. And if you remember, it also has an asymptote, which is exciting. Okay, so make sure you're able to recognize those parent functions. Now, the last thing we need to talk about are the different transformations. All right, what kind of transformations are you responsible for knowing? Well, there are reflections, right? Reflections in the different axes. There are vertical and horizontal shifts. So if it's on the outside and you're adding or subtracting, that is a vertical shift. If it's adding or subtracting on the inside, that's a horizontal shift. And if we are multiplying either on the inside or the outside, that's going to be called a dilation. On the outside, it's vertical. On the inside, it's horizontal. Now, what do we mean by inside or outside? Well, remember those parent functions we just talked about. Inside the parent functions means it's within, in this case for absolute value, the walls of the absolute value function. If it's inside for a square root function, it's going to be inside the square root house, inside the cube root house, inside the second power, inside the third power. Okay, so that's what I mean by the word inside. Whereas outside means that it is not being affected by any of those symbols that represent our parent functions. Okay, when we are adding or subtracting, right, for vertical shifts, up means plus means up, minus means down, straightforward. But when it's horizontal, right, on the inside, it's kind of going to be the opposite of what you think. If I see a plus, I'm going to go in the opposite direction of the positive numbers. If I see a negative, I'm going to go in the opposite of the negative numbers. So that's something you want to keep in mind. With reflections, again, inside versus outside. When it is on the outside of the function, aka the function is just being multiplied by a -1, that's going to be a reflection in our x-axis. Okay, whereas if it's on the inside of the function, inside the square power, inside the square root, that's going to be a reflection in our y-axis, meaning every point that flips to the other side of the graph. Okay, and then vertical stretch or shrink, basically what you want to remember, if it's on the outside, the bigger the number, the more it is stretched out. The smaller the number, the less stretched, the more compressed it is. And it will be the opposite for our horizontal shifts. So let's take a look at how this works. So you can be given any of those parent functions and be asked to identify the shifts. Okay, so what's happening here? Well, here we have the function y equals absolute value of x minus 3 minus 3. First, we need to recognize what is my parent function. Okay, so anytime I look at this, I look for the more general operation. So in this case, it's absolute value. So my parent function is y equals absolute value of x, which is what that first graph shows. So how do we shift or change this graph to represent those changes? Well, first we have to identify. If it is negative on the inside, that means we are going to our right 3 units. If it is negative on the outside, we are going down 3 units. So basically, when we work with parabolas, when we work with absolute value, we're going to start with our vertex, and we are going to shift it to the right 1, 2, 3 units, and 1, 2, 3 units down. Okay, now this happens to be a delta math graph, so it will shift all the rest of the points for you if you need it. And that would, this down here, the non-dashed one, is the translated function. So let's look at one more. Okay, what situation do we have here? Well, we have an inside positive 3, right? So an inside positive 3 means we're going to the left 3 units. Here we have a outside positive 1, which means we are going up 1 unit. So the vertex of this parabola, right, because this is has the parent function x squared, will have the vertex left 3 units up 1. So this vertex will go to here. So everything would follow. Now, obviously, my graph is not going to be perfect because I'm going to do it quickly. But there's one other thing happening here. We have a negative on the outside. That negative on the outside, if you remember, is a reflection in the x-axis, which means all of these points are now going to flip to the opposite side of my vertex. So what was once facing up will now be facing down. So if we take a look, now obviously my graph is not perfect because I didn't have all the points moving piece by piece, but you see we have a very similar graph